Besides the substitutions technique, there's actually another technique called integrations by part, which can be used to solve the complicated integrations problem. Formulas for the integrations by part can be derived from the product's rules of differentiations. Let's say we have a function f of x, where f of x is the product of two functions u of x and v of x. Then the derivative of this f of x is equal to u times the derivative of v plus v times the derivative of u according to the product's rules. So if we integrate both sides with respect to x, then we're going to get duv equal to u dv plus v du. If we rearrange the equations, then we have u dv equal to uv minus v du. So this is actually the equations that we're going to use in the integrations by part. We can use this formula to solve an integral if the integrand is the product of two functions. The steps for solving integrals problem by the techniques of integrations by part can be summarized as this. First, we must choose u and dv, and then differentiate u and get du, then integrate dv to get v. Then substitute u, v, and du into this equation and solve it. So the tips for pick the u is actually we call depend, where if there is any logarithm functions, we will pick it first. Else we take the inverse functions. Then next choice will be polynomial, and then exponential, and finally we will choose u as a trigonometry function. Let's look at the examples now. For this example, we have a polynomial function and a logarithms function. So the logarithms function comes first. In this case, we're going to choose u equal to ln x. And the leftover x dx, we will keep it as a dv. So then differentiate ln x will give us 1 over x, and we can rewrite this as 1 over x dx. Du dx, yes. And then integrate dv. We have v equal to x squared over 2. Okay, at the moment, just drop out the constant c. Then we use a formula just now, which is u dv, this problem, u dv here, equal to uv minus v du. So uv, take this u, take this v, so we have x squared over 2 times ln x, this is the uv, minus v du. V is x squared over 2, du is 1 over x dx. So we can cancel this x here. Then we integrate x over 2, which gives us x squared over 2 divided by 2, so x squared over 4. And finally, plus c here. So this is the answer for this problem. In the next case, we're going to solve the definite integral, where we have a polynomial and an exponential function. So we can see polynomial come before the exponential, so the u will be the polynomial function. So in this case, I will keep u as x and dv as e to the 2x dx. So differentiate u with respect to x, that we get 1. So du is equal to dx or dx is equal to du. Then integrate dv, which gives us v equal to e to the 2x over 2. Drop out the c. Then use the formula u dv equal to uv minus v du. So what we will get should be, sorry, let me put the limit of integration first. So integrate e to the 2x over 2 gonna to give us e to the 2x over 2 again. So what we get should be e to the 2x over 4. And then from 0 to 1, 2. So just substitute the limits of integration in. So we have e to the 2 divided by 2 minus 0 times e to the 0, so minus 0, and minus e to the 2, when I substitute 1 in, over 4, minus e to the 0 over 4. So the final answer will be e to the 2 over 2 minus e to the 2 over 4. So that gives us e to the 2 over 4 and minus plus. E to the 0 is 1, so plus 1 over 4. So this will be the answer for this problem. Let's look at the third example now. In this example, we have exponential and trigonometry functions. And the exponential functions come before the trigonometry functions. So in this case, we will choose u equal to e of x and dv is cos x dx. Then differentiate u, which gives us e to the x, and hence du is e to the x times dx. Then integrate dv, integrate cos x, which will give us sin x, and we drop out the c temporarily. So now substitute into the formula u dv e to the x cos x dx equal to uv, so e to the x times sin x minus v du, so v du, so I have e to the x sin x dx. We can observe now e to the x sin x dx, again the integrand is the products of two functions. So we need to do the integrations by part again. Okay, so in this case, I choose u tutor as a e to the x. And then dv tutor as the, as sin x dx. Then repeat the same process. du tutor dx is ex. So du tutor is e to the x dx. And now only we integrate this to get v tutor. So v tutor is equal to differentiate sin x, we get negative cos x. Now substitute this into the formula. U tutor v tutor, u tutor dv tutor equal to u tutor v tutor minus v tutor du tutor. I just use a u tutor v tutor to distinguish computations in the first set and the second set. Okay, so now is uv. I pick this one, uv. So it's negative e to the x cos x. So this is negative e to the x cos x. v tutor is negative cos x, and then du tutor is ex dx. So negative cos x ex dx. Then I rewrite it as negative ex cos x plus e to the x cos x dx. You can observe that this term is actually same with this term here. So I can substitute the previous formula into here. So previous formula is this. So now I substitute this one. This is actually ex sine x right just now, where this is our u integration for u theta d theta. So I substitute this formula into this one. Then I have e to the x sine x minus negative e to the x cos x plus integration for e to the x cos x dx. Since this term and this term are the same, I just move it to the left hand side. So here is negative, and I move it, I'm going to have plus the same term. So I have 2 times integration for e to the x cos x dx when I move this one to the left. And my right hand side, I have e to the x sine x negative negative plus cos x. So in the solutions for e to the x cos x dx, the integrations of it is equal to, I just move the 2 back to the right hand side. So e to the x over 2 times f sine x plus cos x. Oops, I'm sorry, here actually I should plus a c already. And then plus c. This is the final solutions for this problem. Means in this case, we need to do the integrations by part twice to get the final answer.